day, everyone, and welcome back to the channel. When you look up at the night sky, Jupiter often shines like a brilliant star. We see it as a serene, distant point of light. But if you could get closer, you'd witness a world of unimaginable chaos, a planet ruled by storms larger than our entire Earth. For centuries, we've been captivated by its swirling bands and the iconic Great Red Spot. We knew it was a turbulent place, but we've only just begun to understand the engine driving this incredible weather. The secret, it turns out, might be something we're very familiar with here on Earth, but on a scale that's hard to comprehend: ammonia. Imagine rivers, not of water, but of ammonia gas flowing invisibly through Jupiter's atmosphere. This isn't science fiction. It's the latest mind-blowing discovery from NASA's Juno spacecraft. Juno has been orbiting Jupiter since 2016, swooping daringly close to the planet's cloud tops, peering deep beneath the surface with special instruments. What it found has completely rewritten our understanding of gas giants. It detected vast, concentrated plumes of ammonia gas rising from deep within the planet's atmosphere. These plumes form what scientists are calling ammonia rivers, invisible streams that snake through the planet's different atmospheric layers. It's a weather system unlike anything we've ever seen. So, how does this all work? Well, think about weather on Earth. It's largely driven by water. Water evaporates from the ocean, forms clouds, moves with the wind, and then falls as rain or snow, releasing energy in the process. Jupiter has a similar cycle, but instead of water, a key player is ammonia. Deep within Jupiter, the pressure and temperature are immense. This environment allows for the formation of slushy, ammonia-rich water ice balls, which scientists have nicknamed mushballs. These aren't your average hailstones. They can grow to be quite large, weighing up to a couple of pounds each. These mushballs play a crucial role. They are incredibly effective at gathering up ammonia and water from the upper atmosphere and carrying them deep down into the planet's interior. It's like a giant atmospheric transport system. The mushballs fall, dragging the ammonia with them until they reach a depth where the temperature is warm enough for them to evaporate. Once they evaporate, they release their concentrated payload of ammonia gas. This creates regions deep in the atmosphere that are incredibly rich in ammonia, but what goes down must come up. This is where the real storm fueling action begins. The now gaseous, ammonia-rich air is buoyant. It wants to rise, and rise it does, creating powerful updrafts. These updrafts are like massive fountains of ammonia gas shooting upwards from the planet's depths towards the cloud tops. As this ammonia-rich air rises, it expands and cools, driving powerful convective currents. Convection is the same process that creates thunderstorms on Earth, but on Jupiter, amplified by these ammonia fountains. It generates storms of epic proportions. These rising plumes of ammonia are believed to be the fuel that ignites and sustains Jupiter's spectacular lightning storms and its gigantic, swirling vortices. This discovery of the ammonia cycle helps explain a long-standing mystery. For years, scientists observing Jupiter saw that some areas of its atmosphere seemed to be missing ammonia. They couldn't figure out where it was going. The mushball theory provides a perfect explanation. The ammonia wasn't gone. It was just being dragged deep into the planet's interior, hidden from view, before being recycled back up to power the storms. It's a complete, self-sustaining weather engine. The ammonia gets pulled down by the mushballs, gets released deep inside, and then erupts back up to create the very storms that will eventually form more mushballs. Think about the scale of this. We're talking about a continuous cycle happening across a planet more than 11 times the diameter of Earth. The ammonia rivers aren't just a quirky feature. They are the lifeblood of Jupiter's atmosphere. They are the circulatory system for its weather, transporting energy and material across vast vertical distances. This process shapes everything we see on the surface, the distinct colored bands, the turbulent zones, and the colossal storms that can rage for centuries. The Great Red Spot itself might be influenced by these deep atmospheric dynamics. What's even more exciting is what this tells us about other giant planets in our solar system and beyond. Saturn, for instance, has its own spectacular storms. Could a similar ammonia cycle be at play there? And what about the hundreds of gas giants we've discovered orbiting other stars, the so-called hot Jupiters? Understanding the fundamental physics of Jupiter's weather engine gives us a brand new model to apply to these distant worlds. It allows us to make more accurate predictions about their atmospheres and what they might look like up close. Juno's mission has opened a new window, not just into Jupiter, but into the workings of giant planets everywhere. It just goes to show that even in our own solar system, there are still profound mysteries waiting to be uncovered. A planet we've been watching for millennia still has the capacity to completely surprise us. It's a powerful reminder of how much we still have to learn. The universe is a complex and fascinating place, and with every new mission and every new piece of data, we peel back another layer, revealing a reality that is often stranger and more wonderful than we could have ever imagined. Jupiter isn't just a pretty gas ball, it's a dynamic, living world with a weather engine powered by ammonia. Thanks so much for joining me on this deep dive into Jupiter's atmosphere. If you found this as fascinating as I did, please hit that like button and consider subscribing to the channel for more explorations into the wonders of our universe. And don't forget to ring the notification bell so you won't miss our next video. Let me know in the comments what other space mysteries you'd like to see us cover. Until next time, keep looking up.